So I would like to start my talk with, I dedicate this talk to a memory of Yoichi Iwasaki, who had just passed away on February 2nd this year. And as you may know, Yoichi had been my colleagues at the University of Tsukuba and founder of Lattice QCD in Japan. And while I think while he is famous as a QCD PAX or CP PAX project leader, I think he's also a great theoretical physicist. Actually, Peter Hasenfratz once told me, Peter said, when I thought I found a great idea like RG improvement or maybe non-linear Shiga model some properties, he said, I have always realized that Professor Iwasaki already had the same idea and actually published some paper. So I will miss Yoichi with my deepest sympathies. Okay, so let's start. Today I'll talk about the hadron interaction in Lattice QCD. There are two methods. One is the famous finite volume method. In this method, people calculate spectra of the two hadrons in a finite box. And using Lucia's finite volume formula, people obtain a scattering phase shift. And the other method is HAL QCD method. I will talk about in this presentation. So in this method, we first extract so-called NBS wave function and construct potential or interaction kernel. Then using Schrödinger equation, we extract scattering phase shift. And as you know, it is always better to have two different methods for cross checks. Actually, there was a so-called NN controversy, which is said the finite volume spectra predict both deuteron and dineutron as a bound state at heavy pion mass, like 400, maybe 500, 600. On the other hand, potential method says there are no bound state at heavy pion mass. But fortunately, Lattice QCD community's effort now are resolving this controversy. Actually, this is a presentation by Nicholson at Lattice 2022. And this is a Q cotangent delta. Delta is a scattering phase shift of two nucleons. And this is Q square. And pion mass is about 700 or 800. And previously, the finite volume method predict this result. And this Q cotangent delta cross bound state condition. That means there is bound state here. But recent finite volume spectrum predict this line, this data along the Lucia's finite volume condition. And this Q cotangent delta predict no bound state at this pion mass. This pion mass. And interesting thing is they also calculate potential and extract scattering phase shift using their potential and obtain this band. And as you can see, both agree with each other at low energy data. So that means latest finite volume spectra are consistent with the potential result at low energy. And the conclusion is two nuclei are unbound at heavy pion mass of 700. Okay, this is the plan of my talk. First, I'll explain our method and also compare the finite volume method and our method. And the main part is I consider some divariance, heavy divariance calculation using potential. And in that case, we can also compare finite volume spectrum using potential method. So let me explain formulation. Main quantity in the HAL QCD method is so-called non-beta salpeter wave function, which defined in this equation. So important point is we consider QCD eigenstate. Of course, we cannot have such eigenstate in our hand, but we can define eigenstate and sandwich. We put two hadron operator and vacuum. So this is a so-called non-beta salpeter wave function. And W is the energy of the center of mass frame. An important property of this n-base wave function is its asymptotic behavior. For large R, and if we project it to some angular momentum L, see this wave function behave like sine PR divided by PR. P is the momentum of the relative momentum of the center of mass frame. But the important point is we have some phase change delta L, which depend on PW. And the important point is this is nothing but a phase shift of the L spatial wave in the S matrix. So as you may remember, this wave function form is very similar to the wave asymptotic behavior of the wave function in the quantum mechanics. Therefore, n-base wave function encodes information of scattering phase shift in its asymptotic form. And also, this property is utilized by finite volume method. So once we have this n-wave function, we can construct non-local potential using this equation. So we consider free Schrödinger type operator here with given momentum p square here, and mu is reduced mass. And we have non-local interaction R prime. And it's easy to show such a non-local potential exists. And also this non-local potential does not depend on the energy of PW. However, in practice, it's difficult to extract such a complicated quantity. Therefore, one has to introduce some approximation. So we introduce so-called derivative expansion, and this non-local potential is approximated by local function and its derivative like this. So it's local function with some derivative here. It's some symbolic meaning here. And at leading order, if we take leading order 0, k equals 0, the potential term is obtained, ratio of wave function apply this operator divided by wave function like this. Of course, in this case, this approximation introduces some systematics. And this potential gives exact result at called PW. However, other PW, it's approximation. So we call this exact result is so-called anchor. So this is some demonstration using quantum mechanics. We calculate separable potential in quantum mechanics. It's highly non-local one. And for example, this is the k cotangent delta and k square again. And blue line is exact one, exact phase shift. This model is solvable. For example, if we consider wave function at 0 energy and the exact potential and calculate scattering phase shift, we get this orange line. Or if we take the wave function at very high energy, so k equal mu is some the mass of the exchange particle. So very high energy, we obtain wave function and calculate potential and calculate scattering phase shift, we get green lines. And as you can see, this at the point of the wave energy of the wave function, we obtain exact result here or here, but others is approximation. But if we combine two wave functions and calculate next leading order, we obtain this red line. So this red line reproduce exact one rather well. On the other hand, for finite volume method case, people calculate some energy here and obtain some result here. And if it's 1 point, only one result, and just say it's leading order ERA is just constant or constant. But if you have two, you can get linear extrapolation between 2 points. It's dashed line, red dashed line. So NLO potential is equally good or sometimes even better than NLO, as you can see from this figure. This is some kind of demonstration of our method. And in practice, of course, we cannot have NBS wave function. We have to calculate 4-point correlation function and extract NBS wave function for a ground state. Like if we calculate 4-point function with some source operator and sync to baryon operator, it's some of the NBS wave function. But if T is large, we can obtain NBS wave function at the ground state. However, in practice, it's difficult to take large T, in particular for baryons, and that is a problem. And again, finite volume method also suffer from this problem. That is the reason why people sometimes get wrong spectra for hadrons. So we invented so-called different improved method called the time-dependent method. And again, we consider normalized 4-point function, which we call sometimes R correlator, which is just a ratio of the 4-point function divided by mass of the individual particle, or maybe 2-point function, two-point functions, and which again sum of the NBS wave function. But exponential is different. It's energy minus mass of two particles. Important relation is momentum square, relativistic momentum square is expressed by this Wn plus Wn square and Wn cube, some higher order term. And delta is a mass difference. But if two particle mass is equal, there is no higher order term, and it's closed form. But interesting point is this is sum of the NB wave function, and if we consider potential multiply this quantity and integration over R prime, this must satisfy each NBS wave function satisfy Schrödinger equation type relations. So we have some, and of course in this case, this Pn, we don't know this Pn, therefore we cannot solve this part. However, Pn square is related to Wn, so we can replace Pn square as Wn and Wn square, maybe as a higher order term. But important point is this has, Wn has exponential dependence. Therefore, T derivative gives Wn, second T derivative gives Wn square. So even we don't know Pn square, we can obtain information of these Pn by just taking T derivative. And sum is automatically taken. So for example, using this relation for leading order potential can be obtained from the R correlator multiply delta Laplacian square and time derivative and second time derivative, and divided by R correlators. In this case, we don't need ground state saturation. Only requirement is two nucleon state dominate, no inelastic contribution appeared here. So that T is not so, we don't need such a large T. However, one problem is, here I said we don't need ground state saturation, but we don't have an anchor anymore because this potential mixture of several energy state. Therefore, obtained potential gives some averaged value of the scattering phase sheet according to exact comparing it to the exact scattering phase shift. And our method can be extended to several directions. First is extension to the coupled channel are straightforward, without any assumption of the scattering amplitude. That is very important. And second extension to the more than 3 particle. However, in this case, it's only possible for non-relativistic kinematics, in contrast to the finite volume method. And this is enough for the 3 nucleon forces, but I think relativistic extension are desirable if we have. And also, usually we define the potential in the center of mass frame, but the extension to moving frame are possible, and indeed work for simpler systems, which we recently put a paper on the archive. So let me compare 2 methods. For finite volume method, we can obtain exact phase shift at each PW. But for HAL QCD method, we obtain exact phase shift at 1 value, and we obtain approximated value at other energies at once. And the finite volume case, if we have more data of delta L, more data of the eigenvalue, then eigenenergy, then we obtain more data for scattering phase shift. And in the case of HAL QCD method, we can improve the result by the derivative expansion. And the finite volume cases obtain the correct spectra are essential in practice, and sometimes it's difficult for baryons. And advantage of our method is time-dependent method helps to obtain the result, while in this case, anchor are lost. The anchor means there is no exact result. Result is not guaranteed. And the finite volume method gives used for meson cases frequently, and we have more result on baryons because of time-dependent method. And the finite volume cases, they can use both center of mass as well as moving frames. And we, as I said, we mainly using center of mass frame. And HAL QCD method, in the HAL QCD method, coupled channel extension is very easy. However, for the finite volume method, some model or some assumption on the scattering amplitude is required. And there exist many particle formalisms quite recently, but in the potential cases, it's only for non-relativistic kinematics. And the important point is we may combine both methods to improve accuracy and precision. Let's demonstrate it. So now we consider potential method for dibaryons, and we compare results with finite volume spectrum. So dibaryon is just the 2 baryon bound state or resonance, which has baryon number 2. So in nature, we only know deuteron as dibaryons. And some people claim some dibaryons, but this existence of such a dibaryon is still unclear. So HAL QCD, there are many results from HAL QCD collaboration. First one is H dibaryon, as already discussed in this morning. And recently we published results at physical point using coupled channel case. In this case, unfortunately, we found no bound H dibaryon, and actually no resonances, but we obtain some interaction potential, and we can compare that interaction potential with LHC data for heavy ion collisions. And also delta-delta dibaryon. And in omega dibaryon, we have some physical point result. And today I talk on omega-omega dibaryon and omega CCC dibaryons. Both are almost physical point, not physical point, 146 MeV. So this is a physical point configuration generated on K computer. It's 2+1 flavor gauge configuration on 96 to the 4th lattice with Iwasaki gauge action and non-perturbatively improved order improved Clover Coke action. And this is lattice spacing. Pi mass is 146. K mass is 525 MeV. So it's near physical point. And for omega CCC, we need charm Coke. It's quenched charm using non-relativistic heavy Coke action. And in this case, we use 2 charm Coke mass, which gives the average of eta C and J psi is this value, which interpolated to the physical point. And this is mass of omega CCC. So this is a potential. This red one is omega SSS, so strange Coke. Omega composed of strange Coke, 3 strange Cokes. And this green is omega CCC. And as you can see, attraction is much wider and the repulsive core is much larger for omega SSS, I mean lighter heavy Coke. And we can fit this potential and can calculate scattering phase. This is a 3D plot, sorry. This is a 3D plot of the potential. And you can see height is much, much higher for omega SSS. And the repulsive core is surrounded by attractive pocket, as you can see from here. So this is a scattering phase shift as a function of energy of SSS and CCC. And usually people fitted this K cotangent delta by power of K square. It's called effective range expansion. 1 over A0 is the scattering length and the effective range, etc. And we can calculate, we can fit it, this data and obtain this value. And actually, by solving Schrödinger equation, we found bound state at each channel. So that means there exist dibaryons for omega, omega, and omega CCC, omega CCC. But to calculate actual binding energy, we have to consider effect of Coulomb repulsion. And without Coulomb repulsion, omega SSS, we obtain tiny binding energy like 1.6 MeV and 5.65 MeV for omega CCC. But these has charge -1, so we have repulsion. And at that time, we just consider Coulomb repulsion for point-like particle for omega SSS. So binding energy is reduced by this repulsion and obtain 0.7 MeV. In the case of omega CCC, we consider as more complicated analysis using Coulomb repulsion by considering charge distributions omega. Since charge radius is measured on Lattice QCD, so we use such a charge radius and consider binding Coulomb repulsion between omega CCC. In this case, the charge is -2, so repulsion is much larger than omega SSS. And the binding energy 5.65 becomes 0, means it becomes unbound. And the scattering length is huge, like -20 femtometer. And the ratio it's very small. So without Coulomb, it's positive, but it's become negative because it becomes unbound. So let's compare the result. this maybe skip. It's existing dibaryon system is, say, deuteron. Its ratio of effective range divided by A0 is about 0.3 or 4. And this is dineutron and diproton. It's unbound, but it also has small effective range ratio like this. And the omega SSS, we have this R effective range divided by A0 is a little bit smaller, but by considering Coulomb repulsion, it's much, much smaller. And also, omega CCC cases, this has similar value, but it becomes almost 0, and it becomes unbound. So this figure tells all dibaryon has very small value of R effective divided by A0. That means interaction is near unitarity. Unitarity means scattering length diverges. So it's boundary between bound and unbound. Yeah. Consider finite volume spectrum for this system. So point is, since we have the potential, and consider this operator on a finite lattice. So this is just finite dimensional Hermitian matrix. And there exists the eigenvalue and eigenfunction. So this is a eigenfunction for omega SSS and omega CCC, and eigenvalue like minus 1.8 corresponding to bound state, and some first excited, second excited, third excited. It's similar, minus 5.8, and first, second, third. Also, it's just projected for R space. There are some contamination from L equal 4 because we only use A1, so-called A1 projection, which contain L equal 0 as well as L equal 4, 6, 8. Such a contamination you can see from this behavior. So now, since we have some approximated wave function, and we have R correlator, which is generate source operator and sink operator, and we have R dependence. We can now define so-called projected sink operator for nth eigenfunction. Using nth eigenfunction, we know R dependence, so we projected this operator to this nth eigenstate, and construct projected R correlator using this operator. So just multiply this nth wave function to these guys. So if this wave function is good approximation, and we may expect eigenenergy, correct eigenenergy from this projected wave function. So we can calculate so-called nth effective energy using this projected R wave function. And also, standard R correlator is just summed over all R. That means we project it to 0 momentum state and calculate ratio. And let's compare this effective energy to the eigenvalue obtained by HAL QCD method, this value. So in that sense, this energy is purely finite volume spectrum without using any concept of the potential. Only we borrow wave function from the potential. So this is the result. So omega SSS cases. So this red one is effective energy projected to the ground state. And this red line is our prediction from the potential. So result of the potential and the finite volume spectrum roughly agree with each other. And this is also second excited state. And this green line is our prediction from the potential. And this green square is coming from projected correlation function. So it's finite volume spectra. So again, it's consistent with each other, although error is large for finite volume spectra. And this black one is a zero momentum projected correlation function. So which is between second, lowest and first excited state. So if you naively fitted this correlation function, you obtain this black result. Sometimes it gives very different value. This case is not so bad, but interesting cases, HCC cases. So first, ground state energy is red, which roughly consistent with our finite volume spectrum. But second, first excited state energy agree with our finite volume spectrum. Interesting thing is R correlator gives energy for first excited state, not ground state, even though it's projected to zero momentum. So that means this Wall source strongly coupled to the first excited state, not ground state, probably because this bound state has more compact wave function. So coupling between Wall source to this state is not so large. Actually, yeah. So conclusion is the finite volume spectrum from the correlation function is finite volume eigenvalue with the HAL QCD potential. That is a very good cross-check between two different methods. So in particular, that means systematic from expansion, derivative expansion, approximation of the potential, and the inelastic contribution are well under control for the HAL QCD method. And most interesting thing is the potential for omega CCC correctly reproduce the energy of the ground state, even from a small overlap of the R correlator to the ground state. So even though state doesn't contain much information, much overlap with the ground state, potential correctly reproduce such a spectrum. So actually its size for omega SSS case is overlap of R correlator to each state, its coefficient an, or maybe integrated coefficient is Bn. Its ground state is dominated, others is become smaller and smaller. But omega CCC cases, if ground state is 1, first excited state has 10 or some larger overlap. That is the reason why effective energy dominated by this state and decreasing. And we can also do the higher excited state, second excited state, third excited state. And which, although error is large in such a case, because we don't use any GEVP method, we just one single operator, a single correlation function, and project it to the state. So we have large error, but still it's roughly consistent with our HAL QCD spectrum, which has much smaller error. So let me conclude. Since HAL QCD and finite volume method are complementary, by combining them, we have more confidence on our result of hadron interaction in Lattice QCD. And for example, it's important to understand H divariance in the coupled channel system. And let me finish my talk by presenting ambitious program for improvement. So first, we consider HAL QCD method, and reading of the potential, and calculate eigenenergy and construct projected operator, and give it to the finite volume method and do the GEVP, and extract some energy using GEVP, using this approximated eigen operator. And if this finite volume energy agree with our energy, it's done. So we get correct answer. But if it's not different, we can go back to this information to the HAL QCD method. Since we obtain several good operator, and using this good operator, we can extract higher order term in the HAL QCD method, and calculate next leading order of the potential, and calculate eigenenergy and eigenfunction, and again go back to this GEVP, and calculate improved GEVP. And if eigenvalue agree with each other, it's done. If it's not, go back to potential and come back and repeat this until convergence. That is my ambitious program. Thank you very much.